Hello there, guys. How's it going? Mike coming back at you here with yet another video on discrete mathematics. In the previous video, we wrapped up Chapter 1, our Introduction to Logic and Logical Forms. In this chapter, we are going to get into some more logic, some more logical statements, but they're going to be a little bit more involved. And we're going to begin this chapter with an introduction to predicates and quantified statements. Now, what the heck are predicates and what the heck are quantified statements? A predicate is a sentence with finitely many variables in it and is a statement when specific values are assigned to the variables inside of the predicate. The two expressions that I have here, x plus y is greater than 5, as well as 2x is less than minus 3. These are examples of predicates. They each contain a finite number of variables, and just as is, it may or may not be true. Based on, if we look at this first sample here, based on the values of x and y that we have, it may be true or it may not be true. If x was 4 and y was 5, then yes, this is going to be true. If x is 0 and y is 3, then this is not true. Now, these two quick cases that I just mentioned were if we had just whole numbers being used. But it could be more than just whole numbers. We could be able to choose from more than just whole numbers. We could be able to choose from fractions and whole numbers. We could choose from all real numbers. There's several ways we could choose what are these x and y values. For the second one, this is a predicate here. There's only one variable in it. And again, based on the x value that is chosen, this may or may not be true. If I chose 0, then this predicate would take on a value of false. If I chose minus 5, then this predicate would take on a value of true. So predicates are sentences that can or cannot be true, and you only know which one it is until you assign specific values to the variable inside of that predicate. It's a lot like Schrodinger's cat, except it's not whether or not a cat lives, it's whether or not a sentence is true. So you can think of predicates as Schrodinger's equations, for lack of a better phrase coming to my mind at the current moment. Now, as I said, we could be plugging just whole numbers in for these variables. We could be plugging in fractions. We could be plugging in any real number whatsoever. What I'm saying is that there are various domains that we could be drawing these the values for these variables from. The domain is the set of all values that can be substituted in for each of the variables. So when it comes to these predicates, we're often interested in the values that make a predicate true. And we want to look at all of the values of just say one variable x, or all combinations of values of the variables x and y, say, that make a predicate true, and we think of them in terms of sets. Now, sets have their own notation with them, so we'll see that right now. In terms of symbols, we denote sets typically by uppercase letters. Commonly, capital A, capital B, capital C, capital D, also capital S. Those are the most common letters that we typically use. But ultimately, it doesn't really matter what you call them. And the guys in these sets, these things that are making up the set, these are called elements, we typically denote these guys by lowercase letters. So if an element, x, is in some set capital A, we have a special symbol that we write to say that x is in the set A. And it looks like a funky looking semi-capitalized, semi-lowercase e. It's this guy right here. It is epsilon, which is a Greek letter. And you can think of it as draw a cup that goes sideways and then put a horizontal line through the middle of it. And that's your epsilon. That says x is in A. If x is not in the set A, we draw that same epsilon, but then we put a vertical line through it. As a mathematical expression, to represent the set of all elements of a domain D that make a predicate, which we symbolize by capital P of x, we write, now this is an open set bracket, x is in D, and then a big vertical bar, and then capital P of x. And then we close the set bracket. We have a closed set bracket going on there. And we read that as the set of all x in D such that capital P of x is true. The set of all corresponds to the set brackets there. The x in D corresponds to the x, the epsilon, and then the capital D there. And then the such that gets replaced by the big vertical bar. And then P of x is just P of x. And just one last quick note on the predicate here. We symbolize it by P of x because, again, these predicates contain variables. They contain a finite number of variables. Saying P of x implies that there's only one such variable. If your predicate contained two variables, we'd say P of x comma y, say. Something like that. Or if it contained three variables, we'd say P of x, y, z. Just however many variables you have inside of your predicate. As we said, the domain varies. The domain for a predicate could be numbers, it could be words, or it could be other stuff. It could be other shapes, it could be other symbols, but for the most part for this course, we'll be sticking with numbers. We may do some examples where the domain of our predicate is, say, words, but for the most part, we'll be sticking with numbers. So there are some fairly common domains that we're going to use, and they each have their own special symbol, so I just want to show those to you right here. We have the set of all real numbers, so that includes whole numbers, rational numbers or fractions, and then irrational numbers as well. And that is a fancy R. You can see that it looks like a regular R, except there's another vertical line going on at the end. A subset of the set of all real numbers is the set of all integers, aka the set of all whole numbers. So 0, 1, 2, 3, 4, 5, all the way going up, and then also -1, -2, -3, -4, going on all the way back down. We symbolize this set with a funky capital Z. It actually looks something like that. Looks like a capital Z, except there's another diagonal line going through the middle. Another subset of the set of all real numbers is the set of all fractions, or set of all rational numbers. These are quotients of integers so long as the bottom is not 0. And we denote this set with a funky capital Q. It looks like just a regular capital Q, except on the left outside edge we have another curve in there. And then the last common domain that we will be looking at in this course and also in higher level courses is the set of all non-negative whole numbers. So 0, 1, 2, 3, 4, going all the way up. We're not including negative whole numbers here. And this set of non-negative integers is called the set of natural numbers, and we denote this with a fancy capital N. Again, it looks like a regular capital N, but there's another line on another vertical line on the left-hand side, so it's a little bit thicker there on that one side. So these are the four most common domains that you will see throughout this course and later on in other courses. So that is our intro into predicates, what they are, and how do we represent, and how do we talk about the collection of things that make a particular predicate true. We do them through sets. Now, another way we can work with predicates and these guys is through the use of quantifiers. As we mentioned before, we get a statement by taking a predicate and substituting in a value or a value for each of the predicate variables. We can accomplish this with the use of quantifiers, words or symbols that tell for how many values or elements the predicate is true. And take this little phrase right here, tell for how many elements or values. We're not necessarily assigning a specific number to that with these quantifiers. We're just talking three really main types of numbers, and I put numbers in air quotes. Either all guys in the domain may make it true, maybe only some of them, maybe only some of the elements, maybe only some of the guys in a domain will make a predicate true, and then there may be only one guy in a particular domain that will make the given predicate true. So we'll see what these three quantifiers are. So first one, if you're given a domain capital D and a predicate P of X, a universal statement is a statement of the following form. You see what looks like an upside down capital A, and then X is in D, comma, capital P of X. That upside down capital A is the universal quantifier, and that's the mathematical way of saying for all. So how this is really reading here is saying for all X in D, in this domain capital D, capital P of X is true. Now, a universal statement is true if and only if for every X value in that domain, if you plug it into your predicate, you get something that is true. So every X value that's in D, you would have to plug it into your predicate and find that what you get is true. If and only if capital P of X is false for at least one X value in this domain. So I can find some x value in my domain such that I plug it into my predicate, capital P of x, and the statement that I get is false. If this is the case, then the universal statement is false. And there's a special name for that x value which made capital P of x false. This x value is called a counter example. You'll be hearing this word a lot more as you go on to take higher level math classes, as well as later on in this course. Techniques of proof, abstract algebra, number theory, real analysis. You'll be hearing the word counter example coming up quite a bit. So universal statement, just as a quick recap, think for all x values in a domain, this predicate is true. If the predicate is false for even one x value, then your entire universal statement is false. Given a domain D and a predicate P of x, an existential statement is a statement of the form, some odd shape that looks like a backwards capital E, x in D such that capital P of x, where that backwards capital E is the existential quantifier, which means that there exists or there is. So how this is reading right here is there exists or there is an x value in my domain D such that capital P of x is true. An existential statement is true if and only if P of x is true for at least one x value in the domain capital D. An existential statement is false if and only if the predicate is false for every x value in that domain capital D. So what we're saying here is if you were to take every x value inside of your domain, you plug it into your predicate, and you get something that's false for every one of those guys, then your existential statement is false. There is a third quantifier. Overall, you don't see this guy popping up as much, but you do see it in some cases, so that's why we include it here. The statement of the form, we have the same backwards capital E, but now we have an exclamation point after it, x in D such that P of x. And that backwards capital E with the exclamation point in front of it is known as the unique existence quantifier, which says that there is only one x value in the domain that makes your predicate true. So how do we read that right there? We would read it as there exists a unique x in our domain D such that capital P of x is true. So the exclamation mark in front of the backwards capital E means that it is unique. There's only one guy. Therefore, a unique existential statement is true if and only if there is exactly one x value in D that makes P of x true. If there exists no x values in D that make P of x true, or if there exists more than one x value in D that make P of x true, then your unique existential statement is false. Now, in our next video, we're going to see several samples of these. We're going to do some real world, and when I say real world, I mean in the world of mathematics. We're going to see some real world samples of predicates, these quantifiers, statements involving these quantifiers here, and showing how these things are true or false and all those various cases. So that's what's to come in our next video. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.